So now let's see how do we do that. So let's say I have this is my R1 and this is your 1x device. I will call it Q1. So this is giving me VBE1. I need one more voltage, VB2. So let's have one more diode. VB2. So I want to generate the current in this resistor, if this is R2, to be delta VB by R. So which means this voltage should be VB1. If I make this is VB1, then what would happen? The current which will flow into this device is delta VB by R2, correct? And now I know, so go to the previous case, I know this current, this is VB1, current flowing in this device is delta VB by R2, and if I add another resistor R1, what should be this voltage? Band gap voltage, correct? How can I make this? I cannot directly short this VB1 to this VB1. So how can I make this same as VB1? This node. Yeah. So you just had a op amp, and you, with the virtual short property, you will get that two voltages same. How to find the sign? Okay, so a lot of you don't know actually. So in order to find the negative feedback or find the sign of, so if the sign is given, you can tell whether it's a negative feedback or positive, or if its sign is not given and you are asked to put the sign based on negative feedback, then you can find that. So what you need to do, at the output, give the test signal and move around the feedback and see what feedback is doing, whether it's moving your output in the same direction, or basically test signal, or opposite. If it's a negative feedback, it will try to oppose the variation in the output. So if I, let's say, increase this voltage, now move around this, what would happen? So if this is changing, this both the voltages will change, okay. So and this is VBE. So if you look at the incremental change in the VBE is very small, because if you look at the characteristic of your diode or your bipolar, your collector current has exponential relationship. So if you change the current by a large amount, your VBE will change with a very small amount. But in the other case, the voltage is directly proportional to your IR drop. So you have a series resistor. So any change here, the current change will make a large change in the voltage compared to that, which means if you increase this and if you make this positive, if this is negative, this is positive, since you know this voltage will change more compared to this one, so your output will further increase. So this is creating a positive feedback, which means this should be plus and this should be minus, because if you make the change, this negative will change more compared to positive input, and it will try to oppose any change in the output and make your output stable. Okay. So, that is how you find any feedback system, you can find that way without breaking the loop, you can intuitively find that. Okay. And if you look at the circuit which I have drawn for linear regulators, the reference is connected at negative and feedback is positive. The reason is you have a PMOS at the output. So, that is have another inverting stage and you have to flip the input to make it negative feedback. So, what will be your output voltage? VBG equal to VB1 plus R1 by R2, delta VB is what? Correct. If this is m times, that is 1x. So, your Q2 is m times of Q1, the area. When I say area, it is basically the emitter area. Okay. So, now what is your K factor is R1 by R2, I can define it this as a VB1 plus alpha VT, where alpha is R1 by R2 into VT. And what is the condition for band gap? Delta VBG by delta VT should be 0, which means delta VB1 over delta VT should be equal to what? Minus alpha delta VT over delta T, which will be nothing but K by Q, and we calculated that how much was 86 microvolt per K, that was delta VT, and you have alpha here. I will just add. Correct. Calculate the alpha. And delta VBE by delta T was how much? Minus 1.5 millivolt to minus 2 millivolt per Kelvin. So, let us start with minus 1.5. Okay, we will do the same for minus 2 also, and we will see the range. So, what is your alpha? 17.437. Can you calculate the m from here? Sorry, R1 by R2 into ln m equal to 17.437. If let us say m equal to, most of the time we keep it 10. So, how much is ln 10? 2.3. So, R1 by R2 should be how much? 17.437 divided by ln m. How much? 7.5. So, this is the ratio you require. So, the ratio is more important here, not the absolute value. So, ratio will set your coefficient or the slope of your basically peak voltage, and the value will define what absolute value will do here. Arbitrarily I can choose any resistor like 10 ohm, somebody chooses 10 ohm, somebody 1 kilo, somebody 100 kilo. What difference it will make? Current, so you don't want to burn lot of current because this current will be drawn from your op amp. It's connected to the output of your op amp. So if you make, let's say, order of even 1 kilo ohm total resistance, series resistor, then your current required might be order of milliamps, which is pretty huge. Usually these band gaps are built using tens of microamp. So you will be choosing 100k, 50k kind of numbers here. So if R1 equal to, let's say 50 kilo ohm, then R2 will be 7.5 times of 5. How much is that? Let's simplify it, make it 100k. So, okay, correct. So your current will be very low. So this is R2 and this is R1, correct. So what was the VBG? VBG at room temperature. So VBG equal to VBE plus, what did you have, alpha VT, correct. So how much is the VT? VB is 0.7 volt plus 17.43 multiplied by 26 millivolt. How much is that? No, that's not correct. .453, 0.453, okay. Alpha VT, because VT is at room temperature 26 millivolt. So 26 millivolt multiplied by 17.43 and this plus 0.7, 1.15, yeah, approximately 1.15 volt. Okay, now choose delta VB or delta T equal to -2. Okay. So from this, what will be your alpha? What would be your alpha? -2 millivolt, sorry, divided by how much? 86 microvolt. 23 point? 23 point? Okay, just make it 23. So now VBG will be again VBE plus 23 times VT. So 26 multiplied by 23 equal to 0.7 plus roughly 0.6 volt. Okay, this is 0.5 598, which makes it 1.3 volt. So, your VBG is 1.15 volt to 1.3 volt for delta VB by delta T equal to minus 1.5 millivolt per K to, and depending on the process you might hit any number in between these. So, different process, and most of the time you get 1.25, 1.2 volt. Okay. And this is very close to your, so at room temperature your band gap energy of silicon is 1.12 volt, and at room temperature you are getting 1.15 volt, which is very close to your band gap energy, 1.12 EV actually, electron volt you get, and that is why we call it band gap reference, because the voltage you get is very close to the band gap energy. So, this is your band gap. So, the gist of the band gap here is what you need: PTAT and CTAT, and CTAT is mostly built using VB. So, you just use 0.7 volt there, and then you scaled the VT or delta VB by simply connecting a resistor and flowing a VB by delta VB by R current into that, and you can scale those number, and you can match the coefficients or slope of your VB and delta VB and cancel them, and you get, and so that was just one topology, and you can build a numerous topologies as long as you know how to build a CTAT and how to build a PTAT. All you need to just add the two after scaling them, and you can build like tens of topologies of band gap. Okay, that is why, I mean, if you just Google, you will find numerous topologies of band gap. So, it is not important like how you build it, the most important thing is you get a most accurate reference current. You can do it without op amp also, but it will have a little bit more inaccuracy compared to op amp, because op amp has a negative feedback. So, it ensures that these two branches have the same current, but if you do not have a op amp, then those currents may not match, and you will get some non-linearity behavior in the output, and that will introduce inaccuracy in the. So, if you are not concerned about very accurate band gap and you want a roughly maybe crude band gap, then you can do without op amp, and you can save the current as well as area in your band gap circuit. So, it all depends what you require. Okay, so let us look at another topology of same band gap. Okay, again the same thing. So, this is op amp with the negative feedback. So, these two voltages will be same. So, in order to have the same current in these two bipolars, you need to have these resistors are should be same. So, if I let us say I call it R 3, this also should be R 3, correct. If you have a different, then current will change, and in order to have delta V B equal to V T L N M, you have to make sure that you have the same current, so that the M factor is only coming from your reverse saturation current. Okay. Now, let us look at this. If this is 1x device and this is again choose 10x, the same numbers which we had in the previous case. This is Q1 and this is Q2. So, now just apply simple KVL and see what would happen. What is this voltage? So, if this is your V out, what is this voltage? V out minus V B 2. Okay, what is this voltage? V out minus V B 1. So, what is the current flowing into this resistor? Delta V B by R 1. So, let us make this R 2 and this as R 1, so that we get the same equation what we had previously. So, what is this voltage now? What is this voltage? Delta V B by R 2 into, is this correct? Currents are same, so 2x current is flowing. So, correct. So, your V out is nothing but your band gap voltage, which is V B 2 plus twice of delta V B over R 2 into R 1. So, the only difference is, so if you choose the 10x here, the value which required for your ratio of R 1 R 2 will be half here, because you have a 2x component. Okay, otherwise rest of the things are same, and these are R 3 and R 2 can be replaced with the current sources also. So, if you as long as they are same. Okay. So, you have a MOSFET in the saturation, bias it with the fixed. So, you have a current mirror basically, and since this op amp will ensure that VDS of those two devices are same. So, channel length modulation will not get affect, and you will always get a same current, exact same current. So, or you can use resistor or current. And this is called, anybody knows the name for this particular band gap? Okay. This is named after the guy who implemented this, that's it. So, if you build any new topology, you can name it after your name. So, before I continue with the same, I would like to just fix one typo here. So, okay, because the reason is this voltage should be higher and the bottom side of R 2 should be lower, and you makes 10x, so that V out minus V B will be larger for this. And now you have to flip the polarity of this to make it negative feedback. Okay.